everyone. Hi everyone, and welcome to our physics meetup where we connect teachers and students from Bukidnon to other learners and global experts in physics and education. So we are happy to have here with us almost 200 participants and more adding. So we are delighted to have here with you and we are also happy to host this session with our partner, PINOY Scientists platform. And to guide you through the program briefly, we will start with an opening message, and this will be followed by the introduction to our speaker. And we will have the main talk, the open forum, and then a response, and then we close the session with a group photo. So I know that you are all excited to learn from our speaker. So help me welcome to start and open this physics meetup. Let's start by helping me welcome the initiator and moderator of the PINOY Scientists platform, Dr. Reina Reyes. So a round of virtual applause, please.
Thank you so much, Adele. It's great to see everyone again in the physics meetup, and I'm especially proud and happy to be part of this now as on behalf of the PINOY Scientists platform and community. So our platform aims to connect scientists working here in the Philippines and around the world to people just like you. And so it's really aligned with the aims and advocacies also of the physics meetup. It's been very successful. So happy to be partners here, and also to welcome Gabriel to the PINOY Scientists community. He will be actually taking over the Facebook and Instagram accounts of PINOY Scientists next month. So abangan nyo yun. Don't miss it. So please follow PINOY Scientists on Facebook and Instagram, and you'll get to meet a lot of PINOY scientists. And if you are a scientist or an aspiring scientist, we hope that you will also be part of the community and contribute as we grow this parang special community. So they're looking forward to Gabriel's talk. And so without further ado, we'll pass it on to Merge for the introduction.
Hi, everyone.
Hello.
Hi, can you see my screen? Okay. So our guest speaker for today's physics meetup describes himself in his LinkedIn profile, personal blog, and YouTube channel as an aspiring physicist, an avid musician, and educational photographer and vlogger. Yes, our speaker is not your typical nerd, but rather a very well-rounded, multifaceted man. So he pursued his Bachelor of Science, major in physics, and minor in computer science at the University of Hong Kong from 2012 to 2016. So during his undergraduate years in HKU, our guest speaker was consistently at the Dean's Honor List. And of course, his exemplary performance merited him the Lam Chi Him Memorial Prize in Physics. So this is a scholarship awarded to the best students completing the first year of the Bachelor of Science in Physics degree in HKU's Faculty of Science. And in the following years, he was awarded the Li Po Kwai Scholarship based on his academic merit, leadership, and interest in extracurricular activities of the University of Hong Kong. And in the latter years of his undergraduate BS curriculum, so he enrolled at the University of California, Irvine for an exchange student program. And of course, true to his nature, he again made it to the Dean's Honor List of UCI in the fall quarter of 2014. Our speakers spent the summers of 2015 and 2016 doing research at the European Organization for Nuclear Research, so at CERN, at Geneva, Switzerland. So specifically, he conducted data analysis work for the Atlas experiment at CERN. And this is under an overseas research fellowship by the University of Hong Kong. And after completing his BS Physics degree in HKU, he continued to work in a university for a year. And then in 2017, so he proceeded with his Doctor of Philosophy in Particle Physics at the University of Oxford. And now he is back at CERN So he is looking for dark matter, and along with more than 3,000 researchers working on the Atlas experiment, one of the big particle detectors, the Large Hadron Collider at CERN. And in his free time, our speaker pursues his other passions, which include volunteering in various organizations, voice acting, music, photography, and vlogging. So he actually plays various musical instruments in different styles, and he has recently, or not so recently, but he launched a YouTube channel to document and share his experiences to the world. So, ladies and gentlemen, I am deeply honored to introduce to you our guest speaker for today's physics meetup, Mr. Gabriel Gallardo. Virtual applause.
Hello. Wow, this is a very flattering this is a very flattering introduction. Thank you so much. Good stalking. Good stalking. Right. Let's get this screen share up. Da-da-da-da. See, it was working earlier, and now it's not working. Up. There we go. Yeah. All right. Cool. Is this set up the way I want it to? Yes. Okay. Hi, everyone. So you heard, my name is Gabriel. I'm pretty happy to be here, to be with all of you. I was pretty surprised actually to receive this invitation because, well, I haven't been very active on social media lately, but then I was found out and I was invited to give this talk. So thank you to the organizers for inviting me. This is really, I really enjoy these opportunities to talk about physics and to talk about my research and to talk about what it's like to be someone in my shoes, to people like you who are interested in physics and interested in pursuing a career path something like mine. So what is my story? Perhaps it's a bit different from yours. So I was born in Hong Kong to Filipino parents, and this is a picture of me when I was 15 in school. So I attended local schools in Hong Kong. Unfortunately, this meant that I never really had a really good opportunity to learn Tagalog or anything remotely Filipino in language. So I speak English, and I also speak Cantonese, because if I didn't speak Cantonese, I wouldn't have any friends. I also speak a bit of Mandarin because they taught that in school, and I had to pass the subject. So yeah, I'm slightly trilingual. And then in secondary school, I studied physics because it was something I wanted to do. I remember really stressing in high school about, oh, what subject should I do? What subject should I do? And of course, it was very obvious to me that I really wanted to study physics. And this is because I'm very curious about the world and how it works. So if I thought, okay, if I want to understand the world, I could do it maybe from a social science, economics or psychology or something. But then I thought, well, social science is really just applied biology in a sense. And biology is applied chemistry, and chemistry is applied physics. So I should probably study physics. So that's why I went into physics. And I really liked it. I enjoyed the math. Maybe some of you don't really enjoy the math, but I enjoyed the math at least when I was growing up. Now, not so much. As a PhD student, the math is so hard. But in high school, it was okay. And then after secondary school, well, you heard the introduction. Is this flipping? It's flipping. Okay. So I did my bachelor's at the University of Hong Kong, where I majored in physics and minored in computer science. Now, for those of you who are interested in doing physics later on in postgraduate studies and beyond, I found it really helpful actually to do computer science courses. Well, because, well, firstly, I'm pretty interested in computers anyway, and so it's sort of pursuing something that I really like. But also, I found it really helpful to to bring into my physics work some of the programming skills and the software analysis skills that I learned when I was doing that minor, especially if you're doing experimental physics. So right now, in experimental physics, we have large, humongous data sets, which you have to use computers to analyze. And so knowing a bit of programming and a bit of that is always really helpful. I started working with the Atlas experiment. Oh, where's my pen? This is much more, this is better. So I started working with the Atlas experiment 5 years ago now, exactly 5 summers ago, with the University of Hong Kong. I worked on Atlas, so I'll talk a little bit about that. And then I was lucky enough to start a PhD here at Oxford. So this is Oxford. I happen to live in a house with a big library. These books are not mine. I don't read that much. But yeah, so I'm in Oxford now doing this. And this is a picture of me in my first summer at CERN. So this was taken in August 2015. So I'm even wearing a Philippines shirt here. And you can see this blue thing here is this blue thing here used to be part of the LHC, used to be part of the Large Hadron Collider, and now it's a decoration outside the CERN restaurant. So you can see there's some tables here. This is where people eat. So yeah, this was a pretty cool summer. If you guys ever get a chance to spend a summer at CERN, do it. So CERN has summer student programs, and they accept people from all around the world. You don't have to be European or whatever. You can just apply. If you have an idea or some project that you want to work on, go for it. And it pays really well. It pays like $90 a day, and they give you accommodation, and Switzerland is just a nice place to be in. So if you ever get a chance. Right. So let's talk a little bit about my research. What am I interested in? What do I actually do? So I'm interested in the question of, what is the universe made of? What is the universe made of? And well, most of you are physicists, so you know that matter is made up of atoms, like this pen here. If you split it up in half and then in half and then in half and then in half, eventually you'll come to the atom, which has some structure. You have electrons orbiting the atom, orbiting the nucleus of the atom, and then the nucleus itself can be subdivided into protons and neutrons. And the number of protons that you have defines the element, and then the number of electrons that you have defines the chemical properties of that atom. Then one could ask the question, okay, so if I can split up the atom into electrons and protons and neutrons, can I split it up even further? Can I break it in half even more? And it turns out, at least with the proton and with the neutron, you can. And they kind of look like this. Now, a bit of a disclaimer, this is very much a cartoon. The actual picture is much more complicated and super fascinating. If any of you are interested in studying, what the proton and what the neutron actually looks like, this is a very, very active field of research, and there are tons of PhDs to be given out to hardworking and interested students who are interested in studying this. But for the sake of our discussion, we'll just use this simplified picture. So the proton and neutron are made up of these things here. You have these balls with some letters on them, and then you have these little springy things which sort of join them together. These are fundamental particles called quarks and gluons. So there we go. So you have different flavors. So this is called an up quark here, this blue one up here. And then we have down quarks here, and they also come in different colors, but that's another subject. And each neutron and proton is held together, holds these quarks together by gluons. So these are also particles. They look like springs, but they're actually particles. So yeah, so a neutron would have one up quark and two down quarks. And then a proton would have two up quarks and one down quark. And it's the combination of these things that give the proton and neutron, their mass, and also their electric charge. Okay, so these particles, the quarks and the gluons, as far as we know, are fundamental. They cannot be broken up any further. And then one could ask the question, okay, are there any more fundamental particles? Are there any more quarks? Are there any more gluons or whatever? And the answer is yes. So these quarks, these things come from a theory known as the standard model of particle physics. The standard model of particle physics. Essentially, it's this table of particles that says, okay, all the matter that we know about in the universe is made up of this stuff. And so you can look this up on Wikipedia, what the standard model is. But basically, you have two different types of particles. So on this side, you have matter. So these are particles that make up actual stuff. Okay, you have these, the up and down, make up the proton and neutron. Then you have the electron, which orbits the atom to make the atom. And then you have heavier versions of the quarks. So you have with strange names. So charm top, strange bottom, whatever. And you also have heavier versions of the electrons. So with Greek names. And then you also have these weird things called neutrinos, which are super light and have no electric charge, but they're really important in nuclear decays and such. So in summary, this is the matter. This is the stuff that makes up our universe. And then on this side, we have particles which carry force. So you see the gluon up here, and this is responsible for the strong force. So, and it holds protons together, it holds atoms together, it holds atomic nuclei together. And then you have the photon, which is responsible for the electromagnetic force. And this, all of us are familiar with because so the electromagnetic force is what gives us light. Light is photons, particles of light are photons, or the fact that your fridge magnet sticks to your refrigerator, that's because the photons are there transmitting the electromagnetic force. And then you have these two guys here, which are responsible for the weak force, which is responsible for nuclear decays and other things. And then you have this thing called the Higgs, which is very special. It's a talk in and of itself. This was only recently confirmed to exist in 2012. It's one of the biggest discoveries in our field in recent times. So if you want to ask more about that, I could talk about it later, but it's not really the focus of this talk. And there's also tons of stuff to read on Wikipedia and everywhere else about what the Higgs is and what it does. It's super fascinating. So now that we're here, the eagle-eyed of you will notice, okay, Gabriel, where's gravity? You know, there are four fundamental forces: strong, weak, electromagnetic, and gravity. And where's gravity? And the answer is, well, this model doesn't include gravity because it's too hard. It's described by a theory that is not compatible with this. So this already is one big problem in the standard model, because if we want to try to find a theory that explains everything, then it better explain gravity. But well, the standard model doesn't. So if any of you are thinking about becoming theorists, this is something that you could think about. How do we include gravity in the standard model? Another question that one could ask is, well, Gabriel, I came to a talk about dark matter. Where's the dark matter? And I can tell you that dark matter is not in this picture at all. None of these particles constitute what is known as dark matter, which is why we have to find it. So, okay, what is dark matter? Let's see. My screen share is not updating. Hello. Da-da-da. All right. Let's try something else. Okay, there we go. So where is the dark matter? So we know that dark matter exists because of certain observations that we've made in astronomy and cosmology, such as this one. So I'm not much of an astronomer, so I can't talk too much about what this is. But I can tell you that this is a picture. So let's say Earth is down here. This is a picture of what's known as a quasar. So it's a very bright object, very, very far away from Earth. And what you're seeing is the light from that quasar coming to Earth, sort of in a straight line, because light travels in straight lines. But instead of seeing one point in the middle, we're seeing these additional 4 points around the quasar. And where is that from? Well, this is because there's some stuff between the quasar and Earth, that is acting like a lens, which bends the light, like so, giving this 4-point structure. So this is a phenomenon known as gravitational lensing. So on this slide, here is a cooler picture than what I can draw, right? So you have the Earth down here in the bottom right, and then you have the quasar up here on the top left, and then you have some stuff in the middle, which acts like a lens that bends the light from the quasar to give this strange 4-point image. Now, Einstein tells us that wherever there's energy, wherever there's mass, this can happen. So light will travel in a straight line in curved space-time, where space-time is curved by mass. And we know that galaxies can do this, but we know that sometimes galaxies, they don't have enough mass to give the effect that is seen. And so we say, okay, there's probably some dark matter that we can't see, matter that we don't understand, that's there, that is bending the light. And so that's one theory anyway. Maybe it exists, maybe it doesn't. But for now, people think there's dark matter. So, and I can summarize for you on one slide what we know about dark matter. It explains gravitational lensing and other phenomena. It's electrically neutral because it doesn't glow. It probably has some mass because that's how it has gravity. And then that's it. We don't know what it looks like. We don't know how much it weighs. We don't know if it interacts with anything else. We don't know why it is in the places where we find it. And we also know, if we do some calculations in cosmology, that regular matter, the stuff that makes up you and me, the camera that I'm speaking to, this whole room, or the rooms that you are in, that only makes up about 5% of the universe. So the standard model that I talked to you about earlier, that makes up only 5% of our universe. There's about 25% of the universe that's made up of this strange stuff called dark matter. And then there's another 70%, which is made of something even stranger called dark energy, which is responsible for the expansion of the universe. So, okay, so there's a lot that we don't know. So why don't we try to figure this out? What is this stuff? And today we choose to tackle the dark matter, which is the smaller bit of this pie chart. And how do we study it? Well, there are lots of ways to study it. The way I study it is essentially this. If we can make dark matter on Earth, we don't know what it is. Who knows? But if we can make it on Earth, then maybe we can study it. Maybe we can take a picture of it or whatever. Yep. So how do we make dark matter? One of the places where we try to make dark matter on Earth is here. So this is beautiful Geneva, Switzerland. This is a picture that I found on a travel website, and Geneva is really pretty. Again, if you ever get a chance to go, and someone else is paying for you, like CERN, then by all means, go. It's a fantastic place to be. So some of the important features of Geneva include this, which is a 200-meter tall fountain, and this Lake Geneva. It's absolutely beautiful. Again, if you ever get a chance to go, you got to go. And here's a picture of me in Geneva. So usually the fountain is somewhere here, but it's off now. So yeah, this is me in Geneva in 2015. And under the city, sorry, excuse me, outside of the city, just outside of the city is CERN. So this is one of CERN's visitor centers. This is not actually a scientific research building, but it's a nice landmark. So CERN is right outside Geneva, and you can go there. You can visit in normal times. Maybe not now, but in normal times you can go. And this is me at CERN. This was last January. It was snowing and everything. I took this picture for a scholarship report, so it's not professional or anything. I just wanted to show my scholarship donors that I was there. And then under CERN, so you see this. There's the landmark. Under CERN, under Geneva, about 100 meters underground, is this thing called the Large Hadron Collider. So this is the biggest machine that man has ever built, that humankind has ever built. It's a ring that's about 27 kilometers in circumference, and it runs under the city of Geneva. It also runs into a bit of France, actually. So where I lived in France, around here, when I was living there. Yeah, and you'll see that on the LHC, there are some collision points here. There's 1, 2, 3, 4. So these are points where protons are brought to collide with each other. There are 4 points on the LHC that do that. And I work on this guy, on Atlas. So let me show you a video. Hopefully the video will work. Let's look at this picture first. So this is a picture of what the tunnel actually looks like, 100 meters underground. So normally people like me don't get to go down because I don't work physically on the machine, but people who do go down, they get to enjoy this, and it's pretty cool. There's also a little like electric golf cart that runs along the line of the LHC, so that because it's 27 kilometers, you're not going to walk the whole thing. So they have electric sort of trains and whatever to help people go to where they need to go. It's really quite a sight to behold. CERN has these open days every 5 years. So the last one was 2019. If in 2024 you're on this side of the world, you should definitely go see the LHC. You should definitely go see the LHC. It's totally worth it. And here's a video of how it works. So it's this big ring, right? And you have protons going in opposite directions around the ring at almost the speed of light, And then we bring them to collide inside these big particle detectors, these big cameras. And we take pictures of these collisions like that. And here's another visualization of what that looks like. So this is one of the publicity images that we like to put out. So what's happening here is you have protons going in at the speed of light, at almost the speed of light from both sides. And then when they collide, this produces new particles, just like when two cars crash into each other and there's stuff flying out. In the same way, when two protons hit each other at almost the speed of light, all these new particles will come out, and we try to take a picture of them. So, and the principle of this is Einstein's E equals mc squared. Energy and mass are freely convertible between the two. So we try to convert the kinetic energy of these protons to become the mass of these new particles. And it's pretty cool. Here's another picture, which is a picture of the detector that I work on. This is Atlas. So it's pretty big. You can see here in the bottom is a dude. This is a guy per scale. And the size of this, it's about 25 meters tall and 40 meters long. So it's not a small machine. Again, if you get to go to CERN, you can go down and take pictures of the thing. It's super amazing. I've been once and it was really nice. Again, if you're lucky enough to work on the actual hardware of the detector, you can go down and you can touch it, you can clean it, you can sign your name on stuff. I think, I'm not sure. But yeah. And this is actually, it's a very delicate and well-designed instrument with lots of different layers. I won't go through all of them, but essentially the collision that you see is reconstructed by many, many different layers of subdetectors, and they all work together with lots of software and lots of computing, yada, 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 to try to make the measures that we want to make. And here's a picture of one of the collisions that I actually study. So what is happening here is that you have proton coming in from the left, and then a proton coming in from the right, and then eventually they collide in the middle, and it produces all of these particles, which you can see here. So this is one of the things that I personally study, and that's pretty cool. Okay, so but my research life isn't isn't always looking at pictures. How do I do my job? What does a day in my life usually look like? So I tried to find pictures of me working, and it turns out that when I'm working, I don't really take pictures of myself, except for this one time. This is the only picture that I have of me working at my desk. It's working is sometimes a bit of reading, as you do in academia. I read about what other people are doing, either out of interest, because I'm curious, or because they're working on something similar to me and I need to learn it. There's a lot of coding involved because we have these huge data sets and we have to control their experiment with computers. So I code mainly in C++ and Python, if any of you are interested. And then there's a lot of presenting. So all of this, virtual meeting, Zoom stuff, I'm pretty used to it because on my experiment, we have 3,000 collaborators all around the world. And it's pretty impossible for us to all be at CERN at the same time. So usually people are probably in their own universities, just like you guys are now, or they're somewhere else like me. So we sometimes meet people in person, but oftentimes we also meet them on video. I have to show them my results in this way. There are lots of meetings, and also occasionally I have to write my papers or write this report and write whatever. One of the good things about working in this field for this time is that all I need to work really is my laptop and a good internet connection. So in that way, I've been blessed throughout this weird time that I don't need to go to the office. I could easily do my work from home. At least that's what I thought. But it turns out I really miss my office mates. I really miss having people around to talk to and have coffee with. Otherwise I'm just in my bedroom doing stuff. It's a bit boring, really. So this is my office mate in my first year, so 2 years ago, and she was really great. Unfortunately, I don't have any more pictures of me in the office. It was a bit sad. But anyway, other pictures of what it looks like to be living this life. I've been very fortunate to have the grant money, the scholarship money, to travel for work. So here at the top left, I attended the CERN School of Computing, which is 2 weeks of computers and physics and how to do physics with computers and how to do computers with physics This was held in Tel Aviv, Israel in October 2 years ago. And this was super fun. The lectures were great, the people were great, and Tel Aviv in October is beautiful. I mean, it's not that hot, and you can go to the beach and whatever. It's really great. Here on the right, this was my first ever conference talk, which I gave last summer. So that's pretty much exactly 1 year ago. This was at the International Conference on New Frontiers in Physics. So you've seen this slide earlier. I was talking about one of the projects that I worked on that had recently become public. So that was nice. There are also summer schools that we go to. So down here, this is a summer school that we have for students in the UK every year. And we get to talk about our research. So we have poster presentations and people come up to us and ask about what we're doing. And it's also a great opportunity to meet people and make friends and professional contacts, et cetera, et cetera. So that's pretty nice. Can also talk a little bit about what the output of my PhD is so far. I mean, this is all pretty big stuff, but what do I have to show for it? So my first publication, which I worked on when I was part of Hong Kong U. So I looked for dark matter. So these two red particles here at the end. I looked for dark matter in this particular context. You can ask me about what that was. And the work that I made it into one of the plots. So this red bit here inside the plot, this red bit was my contribution, sort of. I worked on an earlier version of what eventually went into the paper. But anyway, this was nice to finally see something that I worked on, be published. So that was pretty cool. And then after I moved on to Oxford, I started working on some other things. So this one here, which was just published a few weeks ago, actually. We measured the performance of some key system in Atlas, which is used in searches for dark matter. So I talked a little bit about that on my YouTube channel, if you guys are interested. I made these plots. I'm pretty proud of them. And then this was a result that was presented in late July, just this year, which searched for some new physics, which produced 4 or more electrons, 4 or more muons, blah, blah, blah. So I played a pretty big role in this analysis, and it's public. I'm pretty happy about that. And then some other takeaways from my PhD, in addition to all the cool physics and whatever. I always thought, when I spent my first summer at CERN, I really liked it. I wanted to go to CERN because it's fundamental research, right? If I want to study the universe in a very fundamental way, particle physics is the way to go, because that's the smallest you can make stuff, right? That's the smallest component that you can study. So I came for the physics, really, but I stayed for the people. I was so impressed with the people at CERN, because they were nice. It was a good community. Everybody was really passionate about physics, and everybody really enjoyed being around people from different parts of the world. And so one of the biggest takeaways, apart from writing my thesis and getting a PhD, is the friends we made along the way. It sounds like a joke, but it's true. I've had so many opportunities to meet people and to travel to different places. So this is in Tel Aviv in Israel, where I met some friends at the summer school, and then we went out for the day. These 2 pictures were taken at the UK summer school with my friends. At Oxford, I live in a place where it's very convenient to go kayaking, even when we're supposed to be social distancing. So that's pretty nice. This is my conference friends and I in Greece. This was Italy. Again, free vacation. Oxford is a pretty good place to think and to learn and to read. So this is a talk that I attended in my very first week at Oxford, and I'm over here. in the corner. I don't know if you can make me out. So this is pretty nice. And I also had a chance to sing. So I was in this group called the Oxford Commas, and we made a music video 2 years ago. Again, you can check that out on YouTube if you like. This PhD has been really a very unique time in my life where I've been traveling a lot and meeting lots of people and having all these new experiences. And I think it would not have been possible if I didn't do a PhD or if I stayed in Hong Kong. Really jumping out of my comfort zone in this way has really been very rewarding. So, just to wrap it up. So I'm expecting to finish my PhD, my DPhil, quite soon in the next 6 to 12 months. And it's been really rewarding. I've been hunting for dark matter and other new physics. I've been meeting people, learning about the world. It's been really cool. And what's next? Who knows? I don't know. If you're interested in following developments in my career, there's the YouTube channel, of course, which you can follow. I'm also on Instagram, on LinkedIn. I have a website. And yeah, I guess I'll leave you with that. Thanks so much for listening.
Thank you so much, Gabriel, for that very interesting talk. I think a lot of our audience here will have their questions be thrown to you. Are you ready?
Yes, I am.
Okay. We're waiting for some questions, but anyway, here's some questions here. What are the manifestations of dark matter?
What are the
yeah.
Manifestations of dark matter? So earlier in the here we go. So this is one of the ways where we know that dark matter. Not that we know. This is one of the evidence that supports the idea of dark matter, is that we see gravitational lensing, but we know that there's not enough mass to do that. There's not enough mass to do that sort of lensing. So so that's one way that we think it might exist. Another way to infer the existence of dark matter is if you look at the rotation of galaxies. So you expect that galaxies would rotate in a certain way with a certain speed. And its own, how do I explain this? If we don't have dark matter, then our observation doesn't match what we expect. If we have dark matter, that explains why galaxies rotate the way they do. That's another manifestation, I guess.
Okay,
does that answer the question?
Yeah, a little bit, but it's already a good one. The next is Mr. Leighton Mariscotes on the microphone. Can you ask your question?
Hello, po. Can you hear me?
Yes. Hello.
Okay. I will ask a question about the process in the LHC. How do the colliding processes are scheduled? Like when do they schedule it if sound beam is being accelerated, and when is the time that they will observe the collisions? Something like that.
Okay, that's a good question. So I didn't say too much. Let's go back here. Okay, so the LHC, it takes the journey of protons in the LHC starts from a can of hydrogen, because as you know, hydrogen is just a proton and an electron, right? And then you would use an electric field to strip away the electron, so you only have the proton. And then it takes 4 hours in the machine. So it starts here, and then you have an accelerator, which is sort of like first gear in your car, and then you have another accelerator, which is like second gear, and then you have yet this bigger accelerator, which puts it into overdrive. So this whole process to bring it up to the energy that we require takes 4 hours.
Takes 4 hours.
And yes, and we have, I think, 10 to the 13 protons in the LHC when it's fully running. And they go around really, really fast. So in Atlas, we get collisions 40 million times.
40 million
per second.
times. That's what you need to create to see a very visible, distinct observation.
So the reason why we do it so often is because it's very rare that a proton would even react, because protons are really small, and so the chance that one of them hits another one is very small. And so that's why we have a lot of protons and we collide them a lot of times per second, because maybe one of them will do something interesting.
So that means every day you always launch the protons, even right now.
Right. So not every day. The accelerator, they close it for upgrades and maintenance and whatever. So right now, this year, it's closed because they're doing maintenance. But in a data taking year, they would have it on for maybe 4 months.
So every time they make a collision, the computers are just automatically recording them and recording the data sets, right?
Yes.
Okay. Thanks.
Thank you, Mr. Layton. The next question is from Juliana Alincastre. I'll just read her question. You said earlier that you're making dark matter here on Earth. How? And is there a possibility that it could be dangerous to do so?
Okay, so that's a good question. Let's see. Where's the? Okay. No, I didn't want to show this video. Wait, how do I get out of this? Okay. So let's look at this thing here. So this is an example of how one can make dark matter. You would have 2 protons. Can I zoom in? I cannot. Okay. So you have 2 protons coming in, and then through some sort of quantum mechanical magic, is the simple way to put it, the energy of those protons is converted into the mass of these red particles, these X1, X2 particles. And then these X1, X2 then decay, sort of like a nuclear decay, into these X1 particles, which is the dark matter, and then some standard model W and H stuff, which we can observe. So this only works if the dark matter reacts with normal matter. So if the dark matter doesn't react with normal matter, this is completely useless and we can't do anything. But it's really just a theory. It's a hope. It's a dream that we can produce dark matter on Earth. We don't know. That's why we're trying. And is it dangerous? It's probably not, because firstly, a proton going at the speed of light is not actually a lot of energy. I mean, it's enough to microwave your lunch, but it's not enough to destroy the world or anything. And then the second thing is that once the dark matter is made, because it is very inert, it's very unreactive, that it will just most likely fly through most of the Earth and do nothing. So as far as we know, it's probably not dangerous.
Okay. Did it satisfy you, Juliana? But anyway, there's another question. Can you share some of your major discoveries of CERN? From Luis Marquez.
Okay. So some of the major discoveries at CERN. So that's a really big question on the history of science, which I'm not very good at. But some of the big discoveries lately has been the Higgs boson, for example, which was discovered by my experiment and the neighboring experiment in 2012. So this was a a monumental effort because the LHC was built to discover the Higgs boson, and we found it, and now we're studying it, and that's super nice. So that's one major discovery. Some other discoveries that I know about are the discovery of this particle called the Z boson. So this is a particle that's responsible for what's known as neutral currents, which I don't know a simple way to describe it because I don't understand it that well myself. But yeah, this was discovered by a kind of experiment called a bubble chamber by the Gargamel experiment in the 1970s. So that was pretty cool. And then another big offshoot of what CERN is doing is the internet. So the internet, or HTTP, was invented by a guy at CERN because he thought, well, you know, we are in these big experiments of like 200, 300, 400 people, and how do we share information with computers? And so he invented the internet, he made it publicly available, and it forms the backbone of the web as we know it today. So I hope that's helpful for you.
Yeah. Thank you for that. The next question is, how do you know that the particle being produced during the collision of protons is the dark matter? Or what is maybe the signature in the picture?
Right. Okay. So that's a good question. Let's go back to
From
here.
By the way, that's from Kenneth Ian.
Hello, Kenneth. Good question. So dark matter is inert, probably. It doesn't react much with stuff. And so we cannot actually see dark matter with our detectors. We can only guess that it might be there, but we will never know. So a signature that we could look for example, in this example, the L's are leptons, so like electrons, and you see that there are 3 of them here. And then this nu, this little V thing, is also invisible to our detector. So if we were looking for something like this, then what we would try to look for are events with 3 leptons, so 3 electrons, for example, and a lot of missing energy. And the idea of missing energy is that, you know, the conservation of momentum, right? If you have 2 balls that collide like this, then their momentum is conserved in the collision. So what you would see in a process like this is that maybe you would have the 3 leptons going in one direction, and then you would have nothing coming out in another direction. And you would see this as a missing energy, missing momentum. And so if you look for events with 3 leptons and missing momentum, then you could try to see if there's any contribution. So let's say if we look at this plot here. So this plot is it looks complicated, but I can explain it. So we have here the different estimates of what the standard model might look like in the solid colors, and then in the dotted blue line, you have what the dark matter would look like. And then once you have these estimates, which you calculate with math and computers, then you can look at the data, which is the black points, and you're trying to see if there are more events in data than you expect from the standard model. So if there was a lot of dark matter, for example, then this, how do I do this? If there was a lot of dark matter, then this third point here would be a lot higher, for example, which means that you see a lot more events in data than you expect from the standard model. And that would give you a hint that maybe you produced dark matter. Or maybe you didn't, maybe you produced something else, maybe you mismeasured something. It's a tricky process. Okay,
thank you. The next question is from Mildred Garcia. Do you also have a GitHub repository of your codes? What other programming tools or languages do you use in your research aside from Python and C++?
Right. So the biggest software repository that we use is freely available on the internet. So you can go to I think it's gitlab.cern.ch/. I think it's there. So we post most of our a lot of our code onto this thing. And so you can take a look in it and see what languages we use. It's mostly C++ and Python, but we also use JSON sometimes. We also use SQL to interface with databases, and sometimes we write websites with HTML to share our results and stuff. And we also use LaTeX, which is not, it's kind of a programming language, LaTeX to prepare our documents, our papers, and sometimes our presentations as well. And then, was there another question about, oh no, it's the Git and then programming languages, right?
Yes.
Yeah.
So whoever is interested in doing such research, you can start learning Python and C++, at least now. The next question is from John Mark Christian. You mentioned that the speed being used in the LHC is almost the speed of light. Is this a physical limitation as of the moment? Why not use exactly the speed of light?
Right. So this is a very good question. And the answer to that is that the speed of light is, as far as we know, the cosmological speed limit. You cannot exceed the speed of light, ever. So only particles with no mass, like photons, can travel at the speed of light, but particles that have some mass, like you or me or a proton, can only approach the speed of light, and they'll never reach it. So this is a consequence of Einstein's general theory of relativity.
Okay, thank you. The next is, how does the LHC accelerate protons? How does LHC accelerate protons?
Okay,
to almost the speed of light?
That's a super fascinating question. Let me see. Do I have like some white space? Okay. So protons, they have an electric charge. They're positively charged. And what you can do is you can put it in some sort of electric field, like so. If you have an electric field, then you'll know from your electromagnetism classes that if you put a charge in an electric field, then it will accelerate. So this is a simplified version. What actually happens in the LHC is that we accelerate these things using radio frequencies. So you have, hello, how do I go back? So you have your proton, and then you have a radio frequency sort of like this, right? With an electric field pointing this way, whatever, that accelerates the proton. And along the LHC, you have maybe one place where you have this acceleration. So these are called RF cavities, radio frequency cavities. And as the proton goes around and around and around and around, every time it goes through this RF cavity, it picks up a little bit more speed, and then again, and then again, and then again, and then again, until we reach the maximum energy that we can use. And then in addition to this, we also use magnetic fields, strong magnets of, I think, up to 8 Tesla or something like that. We use 8 Tesla magnetic fields to bend the protons such that they go in a circle.
Thank you for that. There are so many questions here, but let's hear personally from Gerald Mancales. Can you ask your question now? Gerald?
Hello.
Is he on the?
Hi, yes,
Yes.
we can hear you now.
Good afternoon, sir.
Hi.
You mentioned earlier about gravity being a mystery up until now.
Mhm.
What is your stand regarding the true nature of gravity? Is it really a particle, or what do you think it might be? Because gravity plays a huge role in the mystery regarding the Big Bang, black holes, and the theory of everything. And I think if we could understand the true nature of gravity, we would we would uh, further understand the true nature of dark matter as well. So what I'm asking is, what is your uh, opinion regarding the nature of gravity?
Right. So I don't really have an opinion, I guess. I can tell you what I think are facts that I know. And that is, so there are four fundamental forces: the strong, the weak, electromagnetic, and gravitational forces. And three of these forces, strong, weak, electromagnetic, are described by the Standard Model, whereas gravity is described by Einstein's theory of general relativity. So in that sense, and general relativity is a very well-tested theory, as we know. We had gravitational waves the other year. So in that sense, gravity is very well described, and it's sort of and fairly understood. However, the problem right now is that the Standard Model of particle physics, which describes the three forces, and general relativity, which describes the fourth force, these theories are incompatible, because when you try to write a theory that describes them all, well, it's just not possible. I'm not really sure what the technical challenges are there, because I've never done the calculations myself. But it's definitely an open problem. So does that answer your question?
I hope it does.
Thank you.
Okay, thank you. Actually, I'm also filtering some questions here. I'd like to ask. I just would like to read those which are related to dark matter. So the next question would be from Sweet Blanche. What are the latest updates on possible candidates for dark matter particles like the WIMP?
Okay. So I see that there are a lot of WIMP or macho or antimatter like questions in the chat. So I can answer. Okay, so for those of you who don't know, WIMPs are weakly interacting massive particles. So this is a weakly interacting massive particles. It's an umbrella term for a lot of different theories. And you see, I attended a seminar about this a few months ago, and I can't remember. I can say that it's possible that they are WIMPs, but right now we're setting very strong limits on how weak the interaction can be and how massive the particles can be. So it's possible. It's an active area of research. I can't remember what macho stands for, but I remember it's also possible that they might be machos. Again, it depends on the parameters of the macho that you're talking about. There's a question about whether dark matter is antimatter, and the answer is no, because antimatter is in fact described by the Standard Model. So if you go back to the table, which you can find on Wikipedia, this describes antimatter already, because in addition to the up quarks and the down quarks, you also have anti-up and anti-down and anti-electrons and anti-this, anti-that. So unfortunately, dark matter is not antimatter.
Okay. The next question is about the unsaved data that were not selected in the 10,000 terabyte is still considered in the whole project. This question came from Isabel Brian Margaha.
Okay, thank you, Isabel. That's a very good question. So for context, if we go back to the LHC, I said earlier that we have collisions at 40 million times per second, but we cannot save all of this data because it's very technically challenging and it's very expensive to take. Can you imagine taking 40 million pictures with your camera per second? It's extremely difficult and very expensive. So what we do is we run these events through something called a trigger. So this is a set of computers. It's kind of like a filter, which filters out the events that we don't want. And we only save events that we do want. And this is about 1,000. We save about 1,000 events per second. And the question, as I understand it, is what happens to all of the events? What happens to all the events that we don't save? And the answer is nothing. They're just lost forever. We try to design this filter such that it saves all of the events that we do want, and then everything else we just throw away because we simply don't have the space or the computing capacity to deal with them.
Okay, thank you for that. Next on the microphone is Warren Tegbabo. We can take your question now, Warren. Is Warren over there?
Hello, sir. Good afternoon.
Hello.
Good afternoon.
Does dark matter exist in every galaxy?
Okay, so that's a good question. Does dark matter exist in every galaxy? Probably. I can't tell you. I think they have different distributions in different galaxies, but I can't tell you what that is. It's not something that I look at personally.
Thank you, sir.
Here's another question from Ken Rick. Are dark matters? It's the same question, but here from John Potaniete, does dark matter contribute to the mass of black holes?
Does dark matter contribute to the mass of black holes? So, as we understand it, black holes are formed from dying stars or from the center of dying stars. And stars, we think, are mostly made up of standard model particles. So that's hydrogen, helium, oxygen, carbon, all that good stuff that we know and love. So initially, at least, a black hole would be mostly standard model, if not entirely standard model particles. But as black holes travel through space, it would be possible for it to suck in some dark matter if it ever existed around it, and that would, then it would be part of the black hole.
Well, thank you. Next on the mic is Renz De Vera. Take it away, Renz.
Hello, sir.
Hello.
Hello.
What do you think will happen if dark matter and antimatter comes to a contact?
Okay, that's a very good question. What happens if dark matter and antimatter come into contact? So we know what happens when normal matter and antimatter come into contact, and that is they destroy each other. So they have some reaction, sort of like you have a negative electron here and then a positive electron there, and then they will just destruct. They will just become light energy. Actually, this is not technically accurate. Let me draw it again. What will happen is this turning into two bits of light. So you have an electron coming in, and then you have a anti-electron. They will meet, and then they will annihilate. They will explode into two particles of light, two photons. Now, what happens when you have a dark matter and antimatter? So the answer is likely nothing, because dark matter doesn't interact with anything. If there was a dark matter particle that hit me in the face right now, most likely nothing would happen. It would just sort of pass straight through me, and I wouldn't even know. And so if dark matter meets antimatter, that same thing is likely to happen. Nothing.
Okay, thank you. Next on the mic is Alfie Ando. Alfie, are you ready to ask your question?
So, am I clear? Am I loud and clear?
Yes, hello.
Oh. Yes,
sir. Before anything else, allow me to say on behalf of my school, Sir Gabriel, thank you for giving us this privilege to be part of this profound topic of yours.
You're welcome.
I have been teaching science, specifically physics, for quite some time already, specifically senior high school. And basically, one of the questions that my students do give me is the following. First, how will the discovery of dark particle affect the state of standard model as it is right now? Are we expecting that in the near future, the standard model of particle physics will be changed or revised? Secondly, what's the thing called string theory doing on this stuff called dark matter? Does string theory has something to do with it, specifically supersymmetric particles? And lastly, sir, the most siguro the most profound question that I have been asked by my students is that why should they care about the discovery of dark matter? How will this generally affect the lives of us, normal citizens? Will this change or revolutionize our concept of life in your opinion?
Okay, so those are pretty big questions. Let's try to answer them. How do I? Ooh, okay. So the first question, let me just write this down. So standard model plus, string theory, and then why. Why should I care? Why care? Okay. So with respect to the first question is what's going to happen to the standard model if we find some new particle? Is it going to change? Is it going to whatever? And the answer is yes. So we, in particle physics, we know that the standard model is incomplete. We know that there should be more stuff. At the very least, maybe there would be dark matter, and then maybe some other things. So if there's some new discovery, some discovery of a new particle, then it's likely that the standard model will change, or there will be some addition to the standard model and we call it by a different name. So that's the first question. The second question relates to the idea of string theory and something called supersymmetry. Oh no, that looks bad. Let's just say Susie. So string theory is the idea that any one of these particles, let's say this up particle, can be deconstructed even further. And it can be deconstructed into strings that are vibrating with some length and some frequency and whatever. And the different strings with their different vibrations give the different particles. So the up would have a string vibrating in one way, the down would have a string vibrating in another way, et cetera, et cetera, et cetera, et cetera. So, and how does this relate to dark matter? Well, we don't know, because string theory right now is a very fundamental thing. It's even more fundamental than the standard model. And unfortunately, it's not testable right now, because so it takes a lot of energy to break up an atom, as you know. If, nuclear fission takes a lot of energy. Nuclear fusion takes even more. And this stuff is, I won't tell you how much electricity the LHC is using. And so to break up the quarks even further requires a massive amount of energy, which we simply don't have access to at the moment. Or if there's another way to look at it, we don't know about it. So for now, string theory is just a theory. It's an idea. You mentioned the idea of supersymmetry. Supersymmetry. And this is actually the theory that I study. This is, in my research, I'm trying to look for supersymmetric particles. And the idea of that is that every particle in the standard model has a supersymmetric partner. So the up would have a sup partner, the down would have a down partner, the top would have a stop partner, and so on and so forth. And supersymmetry, as you hinted before, is necessary for string theory. Where it stands right now is that we have not found any supersymmetric particles, but we're trying really hard. And then your third question is, why should we care? Well, you don't have to care, honestly. I often think that my line of work is honestly just for fun. It's just, I'm curious and I wanna learn some more about the world. And there are some people, or some governments, some schools who are willing to give me money to pursue my passion. Great, that's super. But then there's another argument for fundamental research, which is this. One never knows what happens when you do fundamental research. So you imagine in the 1800s when Tesla and Edison, they were doing their experiments with electricity and whatever, or when Maxwell was writing down his equations, people would think, oh, why do I need to know this? Why do I need to know that, del dot E equals 0, and why do what's this? This is so useless. Why am I doing this? And it turns out that these equations form the backbone of a lot of technology that we have nowadays. And so one can never know. If we find supersymmetry, if we find dark matter, maybe that will amount to something practical in 100 years, 200 years, or maybe the technologies that we develop to find these particles will be useful, just like the internet. So I guess that's why you should care. You don't have to, but I do.
Thank you, sir. Thank you so much.
Thank you for your question.
Thank you, sir.
Thank you for that. Next on the line is Carl Jason Ejos. Carl Jason, you can throw your question now.
Sir, can you hear me?
Yes, hello.
Yes, we can hear you.
Sir, my question is there a way to properly study dark matter?
Okay, that's a good question. There are many ways to study dark matter. Essentially, what we try to do is, how do I draw this? Okay. Essentially, what we try to do is something like this. So we have some standard model particle here, and then we have some dark matter here, and then something that interacts between the two. Okay, so we have the idea of studying dark matter is this. So you have standard model in black, and then you have dark matter in red, and then some force that connects the two. So, if a standard model particle can bump a dark matter particle, it will be because of this guy. So there are several ways to study dark matter at a fundamental level, which is, the first thing is what we try to do is we try to make standard model particles bump into each other and then produce dark matter. That's one way. Another way is to try to see if you have some standard model stuff lying around on Earth and then some dark matter from space hits it, then will it cause a reaction in the standard model particle that we can observe. So in that sense, time would be going from left to right. You have the standard model hitting the dark matter, there's some interaction, and then there's a reaction in the standard model that we can see. That's another way. A third way is you have dark matter in space and they collide. So time will go from bottom to top. The dark matter will collide and then produce some sort of standard model signature that we can detect with our telescopes. So that's the fundamental way to do it. What this actually means is that in the first way, we can use colliders. So we collide standard model stuff to produce dark matter. Maybe that works. The second way is we use, how do we call these? We can use dark matter detectors on Earth. So there are lots of experiments. If you're interested, you can look at the LZ experiment, which is pretty hot right now. These are things on Earth which are just sit there and they wait for dark matter to hit it, and maybe there's some flash of light that we can see. And then the third way is with telescopes or particle detectors. So you can put a particle detector on Earth, preferably in space, and then you just try to see what sort of stuff comes at you from space. And then maybe you can try to figure out if that was produced by dark matter or not.
Thank you, sir. Thank you, sir.
Thank you for your question.
I'm overwhelmed with the questions here, but unfortunately, guys, that was the last questions that we could entertain. However, you can always be updated by Gabriel through his YouTube channel, PPPhD, you know? So you can catch him there, you can post your question there, and probably you can start some conversations with him there. So I'd like to throw this to the administrator now, Adele.
Okay, can we give a virtual round of applause to our speaker, Gabriel? Thank you so much for taking your time to connect with us and also to share your research and also your experience. And can we also give another round of applause to Professor JB Magallanes for moderating our session. Thank you so much. And we apologize if we cannot accommodate all your questions because of the limited time, but please take note that next week, our speaker will take over the PINOY Scientist on social media, so you can ask him questions over there about his research or about his experience as a student. So thank you so much. I'd like to call on Miss Cherry Ponteras. She is a high school physics teacher from Malitbog Agricultural High School in Bukidnon, and she will give her insight about our speaker and about our session for today. So I'd like to call Cherry, Miss Cherry.
Unmute. Hello, can you hear me, ma'am?
Yes.
Agree. Okay. Okay. To our excellent speaker, Mr. Gabriel Gallardo, Bukidnon Physics Society, Central Mindanao University Physics Department, PINOY Scientist Platform and Community, my highly intelligent former college instructors and professors, participants, good afternoon. My task with today's physics meetup is to give a response. First off, it is with a joyful heart and profound gratitude to have you with us today, Sir Gab, as our speaker. Thank you for this deemed to be once in a lifetime opportunity to have you, and thank you that you take us with you as you share your experiences, expertise, and time with us. So we are very honored to have you. And again, thank you for answering all our queries. So congratulations in advance for your soon-to-be graduation. On the other hand, as a physics teacher, today's session inspires me even more to ignite and awaken the curiosity of the minds of my students, encourage and motivate them even more to love and pursue science, well, physics to be exact, and be great scientists and great teachers in the future. Second, congratulations, Central Mindanao University Physics Department for the success of this afternoon's session. It is undeniably a substantial platform to promote inclusiveness among science enthusiasts, connecting teachers and students to global experts in just a click. To end, thank you everyone, and God bless us all.
Thank you, Ms. Sherry. Thank you so much. Would you like to share additional words, Gabriel, to our audience?
I'm just really happy to be here. Happy to hear your questions. If you want to find me, well, you can find me. Just Google me. At least when I Google myself, I'm on the first page. So maybe you'll be lucky too. Happy to take questions. Happy to chat. Anything. Yeah, and thanks for having me.
Okay, thank you so much. I'd like to call on the chairperson of the physics department, Professor Bien Butanes, to wrap up our session.
Good day, everyone. The Physics Department of Central Mindanao University, together with the Bukidnon Physics Society, is very appreciative of your continued support to our physics meetup. Based on our data, our participants are getting farther in terms of geographic allocation, spanning almost the entire country with large delegates from CMU, MSU IIT, UP Diliman, Philippine Science High School, Alubihid National Comprehensive High School, and as far as the UK, France, Germany, Abu Dhabi, India, and Hong Kong. To this, we are humbled and we are motivated to bring more experts within your reach. Of course, this is not possible if not with our session partner, PINOY Scientists, led by Dr. Reina Reyes and Ms. Cami Navarro. We humbly thank them for their support, especially in promoting our event today. As you may know, Physics Meetup is a series of online conversations with invited experts in the different fields of physics. Our goal primarily is to bring these international experts within the reach of college and high school physics teachers, students, and enthusiasts in Bukidnon and the rural areas of the Philippines. We already had several successful sessions, as you may have seen already in our promotion through the CMU Physics Department Facebook page. We would like to also thank our speaker, Sir Gabriel Gallardo, for shedding light on the topic of dark matter. By now, I know that our participants can discuss more of the topic than before. We thank again Dr. Reina Reyes for the opening message, as well as Professor Marjibel Dengal for introducing our speaker, Professor Jingle Magallanes for moderating the Q&A, Ma'am Cherry Ponteras for the response, and finally, Ma'am Mabel Biquiso for allowing us to use her Zoom account. Again, we thank everyone who joins us today, and we are hopeful for your usual support to our next meetup. An announcement will be posted soon on our Facebook page. Before we end, I would like to request everyone to turn on their cameras for a quick group photo. Thank you and God bless us all.
Thank you so much, Professor Bien. Please turn on your cameras and can we do 3 poses so that we can just have this documentation? Okay, are you all ready? Okay, let's have and count. Okay, let's have it. First pose, 1, 2, 3. Okay, perfect. Another one. 1, 2, 3. Okay, last one. We have a lot of photographers in here, screenshot people. So don't worry if you will. Okay. So let's have the last one. 1, 2, 3. All right. Okay, thank you so much once again for joining us. It has been a very wonderful time and we are truly humbled to have you here with us. Please tune in and please like and subscribe our Facebook account, CMU Physics Department, so that you will get to know who will be our next speakers. And again, we thank our speaker, Sir Gabriel Gallardo. Can we give a virtual round of applause? Yeah. We also want to invite everyone to like and subscribe PINOY Scientists. It's on Facebook and also on Instagram so that you can get updated with all the happenings of some of the featured scientists. And you can also ask questions for a week about their experiences and also research. So thank you everyone for joining us, and it has been a wonderful time with you. And we hope to see you again in our next session. So thank you so much, everyone. And if you still have time, you can join us in our short networking. Thank you so much. And now I will have to turn off the live stream. And if you are free, join us in our networking. Thank you.